Exercise 846 is a very cumulative type of problem. The first thing we're going to have to do is figure out what type of mechanism these reactions happen by, and they give us a whole series of them. We have to figure out the mechanism or mechanisms that these happen by, and then we're going to use our knowledge of those mechanisms to predict and draw the products. Now, they're not asking to draw the mechanisms, they're just asking us to predict the products using our knowledge of which mechanisms are being used. So if I say anything in this video that you aren't familiar with, write down the words that seem unfamiliar, and you can feel free to email me, and I'll send you a link to the video in Chapter 7 or 8 that covers that topic. Alternatively, I strongly encourage you to make sure you've mastered all the videos for Chapter 7 and 8 before you attempt this type of problem. Okay, so they want to know the major and minor products for a bunch of reactions. Well, first, we see our leaving group, and let's start with A. We see our leaving group here, and the carbon that it's on is bonded to two other carbons. So that is a secondary carbon. So our leaving group is on a secondary carbon. So if we're just trying to figure out the mechanism, we know that the leaving group is on the secondary carbon, so we're dealing with this row of our table. Now, our nucleophile is really Cl-. Cl- is a weak base and a strong nucleophile. So when we see how that base/nucleophile overlaps with our substrate, we see that the only mechanism that can happen in this scenario is an Sn2 mechanism. Okay, so that's the first step, identifying the mechanism. So we'll set this aside for the next exercise. Now, knowing that mechanism, what is the product that we get? Well, the carbon chain will stay the same, but you'd want to remember that the nucleophile replaces the leaving group for sure. It'll be at the same place, the rest of the molecule doesn't change, but this is also a chiral center, and the nucleophile can only attack from the opposite side. With Sn2 reactions, you get inversion of configuration, and so you would have this bond going away. And that would be the only product for this reaction. Notice they're using dimethyl sulfoxide just to aid the Sn2 reaction. That polar aprotic solvent doesn't encumber the nucleophile. Okay, let's go through the same sort of process for the rest of these, starting with B. So the first step is to try to figure out what type of carbon the leaving group is on. The leaving group is on this carbon here, that's bonded to 1, 2, 3 other carbons, so that is a tertiary carbon. So that, the leaving group, we have the leaving group on the tertiary carbon, so we're going to be dealing with this row down here. Our nucleophile is an OH, NaOH. NaOH is a strong base and a strong nucleophile. Now, the place where that column overlaps with the row that we have, we can see the mechanism. This is only going to give us an E2 mechanism. Whatever products we get, they will be the products we get from an E2 reaction. Okay, well, so that's part of the problem, but now we need to think about what type of products we can get in an E2 reaction. In an E2 reaction, remember the carbon that has the leaving group on is the alpha carbon. Every carbon bonded to that is a beta carbon. And in an elimination reaction, you could form a pi bond to any of the beta hydrogens, to any of the beta carbons, so long as they have beta hydrogens on them. And all of these beta carbons do. So you could imagine forming the pi bond to the carbon going up. You could imagine forming the pi bond to the carbon, to the beta carbon sort of going to the left. You could imagine forming the pi bond to the beta carbon sort of going to the bottom right. Now, there are only actually two different molecules here. This one on the bottom and this one on the top are really the same. if you were to take this molecule here and flip it like a pancake, you would see that it would turn into this molecule up here. So because they're the same, I'm going to erase this bottom one. And those are your two products. Now, in addition to drawing those products, you'll want to say what the major product and the minor product is. Notice that this top one is di-substituted, and the bottom one is tri-substituted. Now, with an E, so we have the tri-substituted one is the more substituted one, that's the Sn2 product, and the di-substituted one is the less substituted one, that's the Hofmann product. Now, with an E2 reaction, everything depends on the base. Here, we have a skinny base, and with a skinny base, the Sn2 product is the major product, the Hofmann product is the minor product. Okay, let's try C. So in this scenario, first thing we want to do, look at the leaving group, that's this carbon right here. How many carbons is that bonded to? 1, 2, 3. So our leaving group is on a tertiary carbon. Now, a tertiary carbon, that means that we're going to be dealing with this bottom row down here. Those are our possible mechanisms. When we look at our nucleophile, or base, it's potassium tert butoxide. The tert butyl group is really an R group, just a carbon chain. It's bonded to an oxygen, and that oxygen has a full negative charge that's being balanced out by a metal cation. So here, the metal cation could be potassium, it could be sodium, that doesn't really matter. It's the tert butoxide that's doing the work. So notice that that is really NaOR. Well, it's KOR, but we have this OR here, this OR group. And so what we're dealing with is a strong base and a strong nucleophile. Now when you have a strong base and a strong nucleophile interacting with a leaving group on a tertiary carbon, the only mechanism you'll get is the E2 mechanism. So whatever products we get, it'll be the products we get through an E2 mechanism. Okay, well, we can redraw this reactant. Remember that where the carbon that has the leaving group attached is the alpha carbon. Every carbon next to that is a beta carbon. And you could form a pi bond to any of the beta carbons so long as they have a hydrogen on them. Each of these beta hydrogens does have a hydrogen on it, so you could form a pi bond in the elimination to any of these. The pi bond always has to be attached to that alpha carbon. So you could imagine having the pi bond go toward the beta carbon on the top. You could imagine having the pi bond go toward the beta carbon to the bottom right. You can imagine having the pi bond go to the beta carbon to the bottom left. Notice that these two top molecules are actually the same. If you take this one and you flip it over like a pancake, you end up with this. So I'm going to erase that since those are the same. And we actually have just two products here. Notice that this left double bond, this one, is di-substituted. Notice that the right one is tetra-substituted. The more substituted one is the Sn2 product, and the less substituted one is the Hofmann product. Well, which one is the major and which one is the minor, that depends on what type of a base we used. We used a bulky base. If you use a bulky base with an E2 mechanism, then the Hofmann product is the major product, and the Sn2 product is the minor product. Notice that we don't have to worry about cis and trans isomers here, because in each case we have a carbon that's bonded to the same thing twice. So this carbon on the top is bonded to hydrogens, 2 hydrogens. This carbon at the right is bonded to 2 methyl groups. Okay. So, let's go through the same thought process for E. First step is to find out what type of carbon the leaving group is on. Leaving group is on this carbon, that's only bonded to one other carbon, so that is a primary carbon. So we have our leaving group in this case. Our leaving group is on a primary carbon. So we're going to be dealing with the mechanisms in this row here. We also have potassium tert butoxide. So we just saw potassium tert butoxide is like this NaOR. It's a strong base and a strong nucleophile. And that means that we're going to be dealing with products coming from two different mechanisms. We're going to have the E2 product, or products, and we're going to have the Sn2 product, or products. Okay, now that we have the products out of the way, or now that we have the mechanisms out of the way, let's see if we can predict which products we'll get through those two mechanisms. First, we can consider the E2 mechanism. Where the leaving group is attached, that's the alpha carbon. The carbon next door to it is the beta carbon. We have only one beta carbon, and so the E2 mechanism will only give us one product. We can only form the pi bond to the beta carbon. So that's our E2 product, and the one other thing to mention, one other thing to note, is that in this mechanism the E2 product is the minor product, and the Sn2 product is the major product. And we talked about the reasons for that in a previous video. So this is going to be our minor product. Okay, let's think about the Sn2 product. With the Sn2 product, we're going to replace the leaving group with our nucleophile. And our nucleophile here is going to be tert butoxide. Remember, the potassium is just there to stabilize it so it doesn't explode when it's in a shelf, in a container on a shelf. So really, our nucleophile is this oxygen with a tert butyl group. So we can redraw the carbon skeleton. Then we can have, instead of the iodine, the oxygen with the tert butyl group coming off. So that is the Sn2 product, and that would actually be our major product in this case. Notice that we don't have to worry about inversion of configuration because we don't have a chiral center here. All right, how about F? Well, first step, ask yourself, what type of a carbon is the leaving group on? That carbon is bonded to just one other carbon, so that leaving group is on a primary carbon. That means that we're going to be dealing with this top row here. What type of nucleophile do we have? NaSH. That is a weak base and a strong nucleophile. So we're only going to get one mechanism here. We're going to get the Sn2 product. So only the Sn2 mechanism will give us products here. So now that we have the mechanism, we can predict it. The Sn2 mechanism just takes the leaving group, so it takes this leaving group and it replaces it with our nucleophile. Now notice the sodium is a metal, so it loses its electrons to the thing it's bonded to. Here, that's a sulfur. So our nucleophile is really SH. So we can draw the carbon skeleton exactly as it is with the 4 carbons that it has. But instead of going to iodine, it would go to SH. And that would be our only product for that mechanism. Okay, G. So here we look for our leaving group. Our leaving group is on a primary carbon. That carbon is only bonded to one other carbon. So again, we're dealing with this top row. And then we can look at our nucleophile. Our nucleophile is sodium hydroxide. That is a strong base, strong nucleophile. That means that we're going to get both the product from an E2 mechanism, and that will be our minor product, and we'll also get a product from an Sn2 mechanism, and that will be our major product. Okay, now that we've identified the products, we identified the mechanisms, we can draw the products. So for an E2 reaction, the leaving group is on the alpha carbon. We only have one beta carbon here, so we only have one place that we can form the double bond to. So we redraw the molecule, being very careful to have the right number of carbons, and then we form that pi bond from the alpha to the beta carbons. So that's our E2 product which is a minor product. Oops. We don't have to worry about cis or trans there because one of the carbons in the double bond is bonded to the same thing twice, 2 hydrogens in that case. And the Sn2 product, for that, we are going to replace the leaving group with the nucleophile. Our leaving group is bromine, so we're going to redraw the same molecule, but instead of bromine, we're going to have our nucleophile, which is OH. So that's our major product, our Sn2 product. Okay, H. So we look at the leaving group. The leaving group is on this carbon here. That carbon is just bonded to one other carbon. So that's a primary carbon. Our leaving group is on a primary carbon, and so we're just going to be dealing with this first row in this table here. Now let's look at the nucleophile. The nucleophile is sodium ethoxide. Sodium ethoxide, we've dealt with a bunch. It is a strong base and a strong nucleophile. So we're going to get 2 products. We're going to get an E2 product, that will be the minor product, and we'll get an Sn2 product, that will be the major product. So now that we've identified those mechanisms, we can draw the products. So with the elimination reaction, in that case, the leaving group, the carbon that's bonded to the leaving group is the alpha carbon. Any carbon next to it is a beta carbon. We only have one beta carbon, and so there's only one place that we can form the double bond here. So I'm very careful to have the right number of carbons, and then we just form that pi bond between the alpha and beta carbons. That's the E2 product, which is our minor product. Notice that we don't have to consider cis and trans here because one of the carbons in the double bond is bonded to the same thing twice. In this case, 2 hydrogens. So that's the elimination product. How about the substitution product? Well, in that case, we're going to draw the same molecule, but instead of the bromine, instead of our leaving group, we're going to attach our nucleophile, which was the OET. So we'll have that same carbon chain, but then we'll have OET instead of the bromine. And so that would be our major product. Okay, let's try I. So here we have our leaving group is on this carbon here. That's bonded to 1, 2, 3 other carbons. So we're dealing with our leaving group on a tertiary carbon. That means that we're going to be working with this bottom row here in our table. As for the nucleophile, we have ethanol. Ethanol is an R group attached to an OH. Right? The eth is just a CH3CH2, so it's a carbon chain. So we have ROH. That is a weak base and a weak nucleophile. So we're going to get 2 products, an E1 product and an SN1 product. And we'll get those in about even amounts. So we'll get E1 and we'll get SN1. Okay. Now that we've identified the mechanisms, we can try to draw the products. First, the E1 products. Well, anytime you have a mechanism with a 1, you have to stop and think about carbocation rearrangements. Will we get carbocation rearrangements? Redraw the molecule, but instead of the leaving group, draw a carbocation on the carbon that the leaving group was attached to. That carbocation is tertiary. Next door, it's primary, primary, and secondary. So it's already on the most stable carbon that it could be, and so there will not be carbocation rearrangement. So we don't have to worry about that, thankfully. So for the elimination reaction, the carbon that has the leaving group on it is the alpha carbon. Any carbon next to that is the beta carbon. In an elimination reaction, you form a pi bond from the alpha to the beta carbon, so long as the beta carbon has a hydrogen on it, which all of these do. So you can imagine for the E1 reaction, getting 3 different products. And you'll see in a second that it's only 2 different ones, but at first it would look like the double bond can form in 3 different places. So you could form a pi bond to the double bond sort of going up, to the beta carbon going up. You could form a pi bond to the beta carbon going to the left, alpha to beta going left. You can go from a pi bond between the alpha and beta carbon going to the bottom right. Those are your three options. And what you'll notice is that these two molecules here are actually the same. If you take this bottom one and flip it over like a pancake, you see that you get this one. So I'm going to erase that one. It's a duplicate. So these are our two possible E1 products. Notice that the one on the left is di-substituted, and the one on the right is tri-substituted. So this is our Zaitsev product, the more substituted one, and the other one is our Hofmann product, the less substituted one. Now, in an E1 reaction, you always get the Zaitsev product as the major product, and the Hofmann product as the minor product. So those are the products of our elimination reaction. Notice we don't have to worry about cis and trans here because one of the carbons in the double bond is bonded to the same thing twice. For the molecule on the left, the carbon on the top is bonded to two hydrogens, and on the right, the carbon at the right of the double bond is bonded to two methyl groups. So those are our elimination reactions. How about our substitution reaction? Well, in that case, you redraw the molecule, and you're just going to replace or substitute the leaving group with your nucleophile. Now, our nucleophile is neutral. That means that at the end of the Sn2 mechanism, we're going to do a proton transfer to take the hydrogen off. And what we'll be left with is just an OET. Notice that that's not a chiral center. This carbon here is bonded to two methyl groups, which are the same type of group. And so we don't have to worry about drawing the racemic mixture of the two enantiomers. So those are your three products there. Okay, for J, first step is to figure out the mechanism. The leaving group is on a secondary carbon that's bonded to two other carbons, so it's secondary. If the leaving group is on a secondary carbon, then we're dealing with this row here. Now we look at the nucleophile, or the base. Sodium hydroxide. That's a strong base, strong nucleophile. So we're going to get two products here, an E2 product and an Sn2 product. Let me write that down for my notes. E2, and the E2 product will actually be the major product, and we'll also get an Sn2 product. Okay, now that we've identified the mechanism, let's think about what products that mechanism gives us. So first, the E2 mechanism. Well, in elimination reactions, the carbon that has the leaving group on is the alpha carbon, and each carbon next door is the beta carbon. We have two different beta carbons, and so we can form double bonds to each of those. So we could have a pi bond going either to between the alpha and beta carbons going down, or we could have a pi bond between the alpha and beta carbons sort of going to the left. Now for the structure on the left, we don't have to worry about cis and trans because one of the carbons in the double bond is bonded to the same thing twice. It has two hydrogens on it. But for the structure on the right, neither of the carbons are bonded to the same thing twice. The one on the left is bonded to a hydrogen and a methyl group. The one on the right is bonded to a hydrogen and a methyl group. The one on the left is bonded to a hydrogen and a cyclohexyl group. That means that comes in two versions. We have the cis version, but you could also have the trans version. There. So those are all of our possible elimination products. Okay, now on the whole, these are the major products, but within this category, we should think about which ones are the major and which ones are the minor within that category. On the left, we have a pi bond that is monosubstituted. On the right, the pi bonds are di-substituted. That means that the molecules on the right are the Zaitsev product, and the molecule on the left is the Hoffman product. Okay, well, this is an E2 reaction, so which one the major product is depends on what type of base we have. We have hydroxide, which is a skinny base. That means that the Zaitsev product is the major product, and the Hoffman product is the minor product. In addition to that, within the category of the major product, the trans product is more stable, and the cis product is less stable. Trans product is more stable because you have bulky things facing away from each other. The cis product is less stable because you have bulky things facing toward each other, and so the trans product is the major product. So altogether, you'll have most of the product will be these elimination products. Among these, you'll have more of the Zaitsev product, and among the Zaitsev products, you'll have more of the trans product. So those are our three possible elimination products. Now let's think about substitution products. In the substitution products, we're going to just replace the bromine with our nucleophile. Our nucleophile is the OH. So instead of bromine, we'll have OH. Right, remember the sodium has a positive charge, so the nucleophile is really just the OH. In addition to that, we have a chiral center here. And when you do an Sn2 mechanism, you get inversion of configuration. So the solid wedge will turn into a dashed wedge. And that will be the minor product. So altogether in this reaction, you would get four products total. And those products are the ones that we've drawn here, using a lot of cumulative knowledge. This is all the knowledge we've gained in the last 2 chapters. Okay, so then for K. First step, let's figure out the mechanism. For that, we have to look at the type of carbon that the leaving group is on. Leaving group is on a carbon that's bonded to 2 other carbons, so that's secondary. So we'll be dealing with a leaving group on a secondary carbon, that's this row here. In addition to that, we have sodium methoxide. Sodium methoxide is a strong base and a strong nucleophile. So we're going to get 2 products. We're going to get E2 products, and those will be our major products, and we'll get Sn2 products. Those will be our minor products. Okay, now that we have the mechanisms, let's think about what type of products those mechanisms give us. First, let's think about the E products. We could form, and this is actually really the same as the previous example, we could form the same sort of 3 products. Because in an elimination reaction, the leaving group, the carbon that's bonded to the leaving group is the alpha carbon. Next door to it are the beta carbons, and in an elimination reaction, you can form a pi bond between the alpha and the beta carbons. So you could form a pi bond going down, or you could form a pi bond sort of going to the left. Notice that in this first one, one of the carbons in the double bond is bonded to the same thing twice. And so that doesn't have cis and trans forms. But in the one on the left, it has different things. It's not bonded to the same thing twice, and so you can have 2 forms, the cis form on top and the trans form. Notice this carbon on the left has a methyl group and a hydrogen, or the carbon on the left, this other carbon is bonded to a cyclohexyl group and a hydrogen. So neither of the carbons are bonded to the same thing twice, and that's why we know that it has a cis and trans form. So these are altogether our major products. Among them, notice that the double bond on the left is di-substituted. The pi bonds on the right are both, the pi bond on the left is mono-substituted. This only has 1 carbon coming off of the double bond. The double bonds on the right are di-substituted. And so these di-substituted ones are the more substituted Zaitsev product, and the mono-substituted is the Hoffman product. Okay, well, which one is major depends on what type of a base we have. We have a skinny base. With a skinny base, the Zaitsev product is a major product, and the Hoffman product is a minor product, when the mechanism is E2. In addition to that, among the Zaitsev product, we have the cis and the trans form. The trans form is more stable, and so the major product, and the cis form is less stable, and so the minor product, because it's forcing bulky things to be on the same side of the double bond. So those are our elimination products. We could also have substitution products. And those, that's what you'd get to picture those. You would draw in the same molecule, but instead of the bromine, you have your nucleophile. And notice that the nucleophile here is really methoxide. The sodium is just a counter ion trying to stabilize that. So we're going to replace the bromine with OMe, and because it's a chiral center, and we're doing an Sn2 reaction, we get inversion of configuration. So the bond that was coming out gets inverted and goes away. So in this reaction, you end up getting these 4 products. The substitution product would be the minor product overall. Okay. In L, the leaving group is on a carbon that's bonded to 2 more carbons, so that is secondary. A leaving group on a secondary carbon, that means we're going to be dealing with this middle row here. Now, the nucleophile or base that we have is sodium methoxide. That is a strong base and a strong nucleophile. And so that's going to give us 2 products, the E2 products, which will be the major products, and the Sn2 products, which will be the minor products in this case. So now that we know the mechanisms, we can use those to predict what products we would get. First, let's think about the elimination products. The carbon that's bonded to the leaving group is the alpha carbon, and each of the carbons next to that are beta carbons. Now in this case, both of those carbons have hydrogens on them, and so you can form pi bonds to both of those. So the elimination products will give us 2 different products at least. Oops. So on the one hand, the elimination product could go, you could make the pi bond from the alpha carbon to the beta carbon below it. Or another option is you could have the pi bond you could have the pi bond go toward the beta carbon to the left. Now notice that in that case, both of those carbons become trigonal planar, so you don't have them coming out or going away from you. Now, in this case, in this first one, we have a carbon in the double bond that has the same 2 of the same thing coming off of it. It has 2 hydrogens coming off of it, so we don't have to worry about cis and trans. But we don't have that case here in this other one. Each of the carbons is bonded to 2 different things. The one on the right is bonded to a methyl group and a hydrogen. The one on the left is bonded to a cyclohexyl group and a methyl group. So we can actually get 2 products there, a cis product and a trans product. Oops. So we have the cis product on the bottom and the trans product on the top. Okay, so those are all the elimination products. Now first, this top one on the left is monosubstituted, and the 2 on the right are tri-substituted. So the ones on the right are the more substituted products, those are the Zaitsev products, and the monosubstituted one is the Hoffman product. Which one is major or minor depends on what type of a base we have in an E2 mechanism. We have a skinny base, sodium methoxide, and so the Zaitsev product is the major product, and the Hoffman product is the minor product. So overall, these products overall, the E2 products are going to be the major ones, Among those, most of them will be the Zaitsev product, so these over here, and among those, the more stable product is going to be the less sterically hindered product. That's going to be the one where the methyl group is pointing away from the cyclohexyl group. And so here, we're going to have this major product here and the minor one here. And that has to do with the crowding, steric hindrance. The cyclohexyl group and the methyl group are on the same side there. They push against each other. Here they're on opposite sides. So the molecule is more stable, and so you get more of that molecule. So those are the elimination products, the E2 products. For the Sn2 products, all you're going to do is replace your leaving group with your nucleophile. Now the leaving group is the bromine, and the nucleophile is just the OMe. So we'll have that OMe there. Notice that the reaction only affects the carbon where the reaction occurs, and because it's Sn2, you get inversion of configuration. So the methyl group that was pointing at us will now be pointing away. So these are your 4 different products that you would get if you did that reaction. Okay, let's go through M. You can see that the leaving group is on a carbon that's bonded to 2 other carbons. That means that the leaving group is on a secondary carbon. And from that, we know we're going to be dealing with this middle row here. The nucleophile and or base that we have is sodium hydroxide. That's a strong base, strong nucleophile. And so we're going to deal with a similar scenario as we were dealing with before, 2 products, E2 product and Sn2 product. The E2 product is major, and the Sn2 product will be minor. Okay, so what would the E2 products look like? Well, the carbon that has the leaving group bonded to it, that is the alpha carbon. And each of the carbons bonded to that are beta carbons. So we have 2 beta carbons here. So we can get 2 different elimination products. The first product would be if you form the pi bond between the alpha carbon and the beta carbon going to the top right. The second product would be if you have a pi bond between the alpha carbon and the beta carbon going down. And notice that if you do that, that methyl group there is no longer pointing away because this is an sp2 hybridized carbon, which is trigonal planar, and so the whole thing is flat there. So those are your 2 possible elimination products. You can notice that the one on the left is di-substituted, the one on the right is tri-substituted, and so the one on the right, the more substituted one, is the Zaitsev product. The one on the left, the less substituted one, is the Hofmann product. Now overall, together, these are the major products. But among these, because we have a skinny base, the Zaitsev product is the major product, and the Hofmann product is the minor major product. We can also do an Sn2 reaction. The Sn2 reaction replaces the leaving group with the nucleophile. And we just have to note that because the leaving group is on a chiral center, we're going to get inversion of configuration. So it doesn't affect the carbon next door, it only affects the carbon where the reaction is happening. And instead of the bond coming toward us, it's going to be coming away, and you'll have the OH there. And so that would be the Sn2 product, which is the minor product in this case. So in this reaction, you would get all 3 of those products. Last but not least, we have N, and this is actually very similar to the one we just did. So here you can see that the leaving group is on a secondary carbon, it's bonded to 2 other carbons. So we're going to be dealing with this middle row, and our nucleophile again is sodium hydroxide, which is a strong base, strong nucleophile. So our mechanisms will be the same as we had last time. We'll have the E2 mechanism, which is our major, will give us our major products, and we'll have the Sn2 mechanism. That'll give us our minor products. Okay, let's think about the elimination products first. The carbon that the leaving group is bonded to is the alpha carbon. Next door you have the beta carbons. When you do an elimination reaction, you're forming pi bonds from the alpha to the beta carbons. And on the one hand, you could have the pi bond formed between the alpha and beta carbons going up and to the left. On the other hand, you could have the pi bond forming between the alpha and the beta carbon going down. And notice that that is now trigonal planar. This carbon here is sp2 hybridized and so trigonal planar now, so you don't have it as a solid wedge anymore. So those are your elimination products. You'll notice the one on the left is di-substituted, the one on the right is tri-substituted. So the more substituted one is the Zaitsev product, the less substituted one is the Hofmann product, and because we're dealing with a skinny base here, the Zaitsev product would be the major product of those two, and the Hofmann product is a minor product. Altogether, these E2 products are your major products. For the substitution reaction, we're going to be, for the substitution reaction, we're just replacing the bromine with our nucleophile, which is the OH. And we get inversion of configuration, so the bond is going away instead of coming out at us. So I went through these more or less, I went through these at a steady pace, a little fast maybe. If anything did not make sense, that means that there was a concept, there was a previous video whose material you had not completely mastered. Everything we covered here, everything that I did more or less quickly, we spent a lot of time on going in detail through in previous videos. So I strongly encourage you to go back and review those, and if anything doesn't make sense after that, definitely reach out to me, email me, and I'd be happy to work with you to explain